Hello everybody, in this video we are going to do more problem solving with generating functions. And the following problem is we want to prove that this summation is equal to 4 to the n. And this looks very scary. The only thing I know about connecting sums of binomials and powers is, well, the binomial theorem, I guess, is a general rule. Um, and I guess the consequences of that, or what I'm thinking of, is that if you look at any row of Pascal's triangle and you add up the numbers, then you get 2 to the n, basically, for whatever the row number is, the row number's n. Um, and but this is, we're multiplying here, and this looks like a beastly left-hand side, right? But a very, very nice simplified right-hand side. Now, we kind of notice that these two terms that we're multiplying have the same general structure. It's 2n choose k, but here instead we have n minus k. We're replacing that for n and k. Um, and that kind of reminds me of what I talked about in a previous video on convolution, where we took a sum and it was f of k times g of n minus k. And we summed that up. And we showed that this actually gave us sort of the nth term of a polynomial, say p of x. And this polynomial this polynomial was the product of the generating functions for f and for g. And so, as it turns out, what this is saying is that we have some polynomial, right, p of x, that is the nth the nth term is always 4 to the n. Okay, so we can see if we can find that. What we're saying is that that is equal to this sum, right? So, which means that basically the product of the generating functions for f and for g has to equal that polynomial. But we're lucky here because we know that f and g are actually the same functions because we're taking the same thing, but we're just substituting in minus k. So, so what I'm saying here is that we have the same function, f of k, and we're saying that if we multiply it with itself, we get p of x. That's what we want to prove. And so f of k, right, this is, or I guess I should write f of x here, but this f of x is the generating function for 2n choose n. Um, and so we want to show that that generating function squared equals p of x, but let's first figure out what p of x is, because this looks very simple, right? And so let's think, if we have a polynomial that generates powers of 4, right? If we just start writing down the first few terms, we get 1 plus 4x plus 16x squared, and so on, right? And we sort of notice that this is 1 is 4x to the 0, 4x is 4x to the 1, and 16x squared is 4x squared, right? So this polynomial is actually just equal to 1 over 1 minus x, but instead of an x, we have a 4x. This is our generating function for powers of 4. So we have uh, this here. Wait, hold on. Yeah, okay, that's all right. So p of x is 1 over 1 minus 4x, which means that we want to show that f of x is equal to the square root of this, to 1 over square root of 1 minus 4x. We want to show that this function generates 2n choose n. Alright, so how can we do that? Well, in the same video where I introduced this convolution sum, right, I also showed what the negative or the generalized binomial theorem is, right? And so what this is doing is we have 1 minus 4x to the negative 1/2. And let's see. Right. So and this looks like our 1 minus, or really we had a 1 plus x to the r, and we were expanding sums of this form. So we know that this here is equal to the infinite sum, as k goes from 0 to infinity, of k minus 1/2, choose k, times 4 to the k. And so we can look at just one of these sort of types of things. So if we expand the binomial coefficient, right, in the bottom we have k factorial. And we know that on the top we're going to have the first k sort of things that look like this. So like k minus 1/2, k minus 3/2, so on, until we get, well, first I want to talk about if k is just equal to 0, then we're going to have negative 1/2 choose 0, and we stated that that would be 1. Anything choose 0 is 1. And then times 4 to the 0 is also 1. So we know that the first thing is going to be 1. So we're going to assume k is greater than 1 here, right? So k minus 1/2, that's at least 1/2. So basically we take the first k numbers until we get to 1/2, right? And we divide it by k factorial. And then this is times 4 to the k. So this is the general term for k is greater than 1. So what we can do is actually, instead of 4 to the k, we can write this as 2 to the k times 2 to the k. That's valid. And we can, since we know we have k terms up here, so we can take each of these numbers, right, or each of these k2s, right, we have k2s here, and we can multiply each term in the numerator by 2, so we get 2k minus 1, 2k minus 3, dot, 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 all the way until we get to 1, right? And this is starting to look more like something that would be of use to us, that looks more like an actual binomial, or like, because we're now we have all integers, but these are all odd integers, right? This is, I haven't introduced the double factorial, but this is 2k minus 1 double factorial, which is the product of all the odd integers, right? But what we can do here is we still have this other 2k, and we want to show that this is actually just equal to 2k choose k, right? That's what we want to show. And if we expand this, we don't get a 2 to the k here, so we can still use this 2 to the k at our expense. And really this is where we think, okay, we have all these odd integers. We have all the odd integers we need, actually. Now all we need is even integers. And how many even integers do we need? We need k of them. So that's nice. We have this 2 to the k here, and we need k even integers. But how are we going to get them? Well, and what integers am I talking about? Well, the numerator needs to be 2k factorial, which is 2k times 2k minus 1 times 2k minus 2 times 2k minus 3, right? So on and so on. But we need all the even ones. So we need, well, first we need to start with 2k, then we need 2k minus 2, right? And we go on and on until we get to 2. But if we factor out a 2 out of all of those, so I'm just going to write 2 and then this whole list. So we get k minus 1, dot, 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 1, right? The product of all these integers is just k factorial. So this is equal to 2 to the k times k factorial. And we have our 2 to the k, so we just need another k to k factorial. So what we can do is multiply the top and bottom by k factorial. So this 2 to the k factorial gives us all of our even integers so that our numerator becomes, instead of just the odd integers, we get all of the integers from 1 to 2k. So we get 2k factorial on the top, k factorial, k factorial. So we've proved that 1 divided by the square root of 1 minus 4x generates 2n, choose n. And so now um, we know that this convolution sum, right, will actually give us 4 to the n every time, because this is the nth term of this squared, so and that ends up being 1 over 1 minus 4x, which generates powers of 4. Whew. So I hope you enjoyed that. Thank you for watching this video, and I'll see you in the next one.